I'm Daniel Norwood, an applications engineer in our high power drivers team. I work on our isolated gate drivers, specifically supporting any customers that are using our SPI programmable protection drivers in traction inverter systems. So I've worked with a variety of different customers to apply our isolated gate drivers in their systems for maximum efficiency and reliability. Today, we're going to be talking about key design considerations for improved efficiency and power density in 800-volt silicon carbide traction inverters. And we'll get into the agenda in a minute. And with that, let's get started. So our agenda today will start out looking at traction inverter functionality and trends in EV, HEV, so that's electric vehicle and hybrid electric vehicle. We'll look at why electric vehicles are an important topic today, and then what a traction inverter is and how a traction inverter really helps meet a bunch of electric vehicle goals, and that leads to key traction inverter design considerations. We'll then talk briefly about how isolated gate drivers with integrated protection, monitoring, and efficiency features can help meet the overall electric vehicle goals and contribute to the design considerations. And finally, we'll close with a deep dive into adjustable gate drive strength and how traction inverter operating conditions impact power switches and the switching losses, how the adjustable gate drive strength is implemented, both the concept and design, and then also throughout that, we'll show some waveforms and experimental test data showing the impact of adjustable drive strengths in a real system. So starting out, electric vehicles are a big topic today, as I'm sure you know if you're joining this seminar. And cost and driving range are still the biggest hurdles. Even as EVs are gaining popularity. You can see here that the number of consumers who would consider purchasing an electric vehicle varies a lot, but is trending upward. In the US, it could be up to 30%, in Europe, up to 60%, and in China, one of the biggest EV markets, up to 70% of consumers would consider purchasing an EV. But the electric vehicle purchase price and driving range are still some of the biggest hurdles to wider consumer adoption. So as designers, if we can reduce the overall cost while also improving the driving range, then we're going to reach more people. To drive that home, there's a cost gap of about $12,000 between a traditional internal combustion engine vehicle today and the available electric vehicles. We need to work to provide value for that cost difference or reduce that cost difference both through range and cost. And there's a variety of ways we can do that. At TI, we want to drive vehicle electrification forward, both for hybrid and electric vehicles. So we'll use our continuous innovation, our technology and expertise to help maximize driving range, making electric vehicles more affordable and enabling faster charging and safer operation. All of those go together. So this leads to 4 goals. The first is maximizing drive range. Maximize drive range with accurate reporting of state of charge and state of health of the battery, and then also by reducing the power consumed to get the same performance. That's increasing the efficiency of the traction inverter by reducing extra losses. We want to improve EV charging by designing smaller and more efficient systems enabled by high performance topologies, advanced features, and advanced architectures. We want to make EVs more affordable with a variety of pin-to-pin compatible automotive qualified devices to support different cell chemistries and vehicle architectures. That includes in the traction inverter, different types of power modules. You can have a traction inverter design with our gate drive circuits that can use either IGBTs or silicon carbide, allowing easy dual source and better affordability. Throughout all of that, we also want to enable safe operation. It's important to improve reliability and performance of powertrain systems with optimized thermal management and enhanced electrical safety. We want drivers and consumers to be comfortable with electric vehicles and prevent any unnecessary injuries, which leads to a huge importance of safe operation. So to introduce traction inverters to those that are less familiar, a traction inverter can be thought of as the core of an electric vehicle. It's what takes the voltage from a battery, so your 400 volt or 800 volt battery, and then converts it to an AC current, which actually turns the motor. So it converts DC to AC and directly controls the speed and torque of the motor, which is the speed and acceleration of the overall car. So this component, the traction inverter, directly impacts both the efficiency and reliability of the vehicle. And as such, it is one of the key areas of design to really improve electric vehicle experience and cost. So the traction inverter is key to achieving all of those design goals we mentioned earlier. We've seen several trends in inverter and motor control. But to address those, let's first look at this block diagram. So we have a block diagram of what a traction inverter includes. You've got the low voltage battery, which provides power for the logic and control. And then DC-DC converters to get the power across the isolation barrier. We've got the high voltage batteries connected to the actual power stage. We've got current and voltage sensing, isolated digital signals for ADCs, and other signals and monitoring. We've got digital processing, CAN, PWM, GPIOs, ADCs, MCU cores, position sensing, CAN, many different components, all of which can contribute to a well thought out design. In this presentation today, we're going to be focusing on the power stage, which includes the digital isolation, some logic, and then the high side, low side driver and actual power stage itself. In this area, we've seen a variety of trends. One of the most significant is increasing power levels. It is no longer sufficient to have 100 kilowatts of power from a traction inverter. More typical is 300, 350 kilowatts up to 500 kilowatts, which always comes with increased design challenges as we want to get more output without increasing costs as much as possible. We're also seeing higher battery voltages. We're no longer seeing 400 volt as the normal, 800 volt is the new normal, but with an 800 volt system, you have to design for 900 volts or 1 kilovolt because when a typical 800 volt battery is fully charged, its voltage will actually be slightly higher. And then we're also seeing a trend toward higher power density, up to 50 kilowatts per liter, as a result of system integration and the desire to have small systems in the vehicle and reduce overall weight. So this is a key consideration and leads to additional challenges when it comes to electromagnetic compatibility and power stage design. Finally, one of the key trends is maintaining safety and reliability, even as power levels are increasing, voltages are increasing, and increased power density. It becomes even more important to make sure that you can handle both protection of your expensive components like the power modules, but then also safety and making sure the traction inverter goes to a safe state and the car goes to a safe state to prevent over torque or harsh braking, anything that could cause injury or harm to the drivers or passengers. Again, we want to make sure that consumers are comfortable with electric vehicles, and part of that is really careful design. To summarize that and really look at some of the key components, we've put together some key traction inverter design considerations and then related those both to the electric vehicle goals we mentioned earlier and the specific inverter subsystems and how they can be reached with careful design of the inverter subsystems. So first, looking at the electric vehicle goals of maximizing electric vehicle range, improving electric vehicle charging, making electric vehicles more affordable, and enabling safe operation. All of these are tied into the design considerations. Efficiency reduces the amount of power the traction inverter consumes for a given output. So that directly contributes to maximizing electric vehicle range, improving charging by getting more distance per charge, and then also making EVs more affordable by reducing the size of the battery needed. It also reduces thermal needs and the size of cooling mechanisms. The next is cost. Cost is a key component for consumers and is absolutely essential to making electric vehicles more affordable. The cost of each component and the number of components all contributes to the overall cost of a vehicle. So by simplifying design, we can make electric vehicles more affordable. Size. To make electric vehicles more affordable, it's also important to get smaller size, which reduces overall material cost and points toward greater efficiency. And then protection and reliability both enable safe operation by protecting the power module and traction inverter itself from any damage, preventing overuse automatically, and then also making sure that it will last for a long time and the drivers and consumers will not be surprised by any extra maintenance or even worse, dangerous conditions such as unexpected torque or braking. And a variety of different inverter subsystems contribute to these design considerations, which then contribute to the goals. These include the controller and MCU, which generates the PWM and the output current of the traction inverter, the bias supply, which provides isolated supplies to switch the power modules, feedback loop, which lets the MCU know what the output current is for precise control, then the more physical design of the bus bars and power modules and the corresponding parasitics, and finally the gate drive. So this is where we'll focus a lot of our attention today. The gate drive is an essential part that directly contributes to efficiency, cost, and the protection and reliability of a system. So focusing on that last component, the gate drive, increasing integration of the gate driver has a big impact on the system, addressing the efficiency, the safety and reliability, and many other factors contributing to those same traction inverter goals. So modern gate drivers integrate many features such as isolated ADC sensing, power module temperature sensing, DC bus monitoring, but also several protection features, including DSAT and overcurrent protection, bias supply monitoring, gate voltage monitoring, as well as including safe states. So in response to any other fault, the gate driver can be programmed to go to a safe output state to maintain safe operation, even if something goes wrong in the system. Built-in self-test also work toward that. In the case of a random failure, built-in self-test helps the driver and the system to know that there is a problem so that it can be accounted for. And then one of the final features is variable gate drive strength, which will be the focus of the last part of this presentation, to really demonstrate how it can contribute to efficiency, reduce system cost, and increase reliability. Looking at the figure on this slide, we have a typical power switch and then a list of all the different features and how they impact the overall system. So first, looking at the actual gate drive, this includes the turn on and turn off, as well as some protection functions. So it controls how quickly the power module or silicon carbide switch turns on and turns off. Then we have the protection here, the DSAT and overcurrent protection, and sometimes also drain source overvoltage detection and other features. These all will report a fault and put the output in a safe state, while also alerting the MCU that there's a problem so the entire system can go into a safe state. We also have analog signal monitoring, which can be used for bus voltage sensing or temperature sensing. Most common would be temperature sensing. And all three of these features are included in our UCC 217 family of gate drivers. Going beyond these protection features, we have some additional protection features in our more advanced gate drivers, UCC 587X and UCC 588 families. So both of these families integrate SPI, which allows detailed programming of the device to get the protections down to exactly what you need and any arbitrary safe state, whatever might be necessary. They include built-in self-test, gate voltage monitoring, and ADCs, as well as active short circuit, or ASC. ASC is essentially a second input to the gate driver that allows safety logic or a safety controller to take over if there's a failure in the primary control logic, putting the gate driver and the entire system in a safe state. We also have in our most recent driver, UCC 5880, this nice adjustable gate drive strength feature, which we'll dive into in just a minute. But that feature, again, has direct relationship to efficiency and reliability as well as cost. Now, diving into one of the key parts of this presentation. What is variable gate drive strength? A traditional gate driver includes a pull up and a pull down. So Q1 and Q2 in this figure that then push current through an R-on or RF gate resistor. So these gate resistors, R-on and R-off, can be adjusted to control the turn on and turn off current or turn on and turn off time of the power switch. So the drive strength is determined by the impedance of Q1, Q2, and the internal gate driver, plus any external gate resistance, R on and R off. This is not adjustable in real time, but the on and off resistances can be selected for a system to make sure that the system operates at a safe state. With variable gate drive implementation, you have the same turn on and turn off, but instead of a set gate resistance, you have a set gate resistance in series with a gate resistance and a power FET that can be turned on or turned off to change the effective on resistance or off resistance of the gate drive. So this adds external components, which adds cost, but lets the turn on and turn off time of the silicon carbide switch be adjusted, which leads to several benefits. We'll get into more depth later, but essentially, when you can adjust the gate drive strength, you can optimize your switching losses and drain source overshoot depending on other conditions in your system. Taking a step beyond this discrete implementation, this can be integrated into a gate driver. For our driver, UCC 5880, we've implemented it with this figure you can see. We've got a dual split output power structure. So instead of one turn on or FET, we have two pull-ups and two turn off FETs, each of which has an individual gate resistance, which can be programmed for different turn on, turn off drive strengths, depending on the inputs to GPIOs or SPI. This reduces the cost and complexity when compared to a discrete circuit, and is much easier to control. It doesn't require an external digital isolator or external FETs, meaning that it is a lot easier to implement in your system and change your control logic to really get the maximum effect. So we've talked about how variable gate drive strength is implemented between these different figures and splitting the output structure, but why would you actually need it? So we get into that on this slide. Power switch transient elements include the drain source overshoot, so that's how much above the bus voltage the drain source voltage of the power switch goes. And then also the switching losses, which is how much energy is lost each time the power switch turns off or turns on. So gate drive strength directly affects the switching speed, which is how long it takes for the gate driver to turn on or turn off. And switching speed then directly affects the switching losses and the drain source over voltage. So you can see the switching losses first. So with a strong drive strength in this top portion, the turn on time of the gate driver is relatively short. And this means that the turn on losses represented by this gray area, are relatively small, as compared to weak drive strength, which has a longer turn-on time and as such greater area of this gray area, which leads to increased turn-on energy. We've quantified this right here for you. So with a weak drive strength or 5 ohm drive strength, you get a turn-on energy loss of about 40 millijoules and a turn-off energy loss of also about 40 millijoules. But with a strong gate drive strength or 1 ohm gate resistance, you get a turn-on energy loss of only 16.5 millijoules and turn-off energy loss of 20.2 millijoules. That's about 50% savings, which is quite significant. But there is a trade-off, and that trade-off is the drain source peak voltage. As you can see, with high drive strength, the overshoot is significantly higher than with low drive strength. Quantifying this, with weak drive, you get about 118 volts overshoot. So with an 800 volt bus, that's 218 volts of overshoot. But then with strong drive strength, you get 1,157 volts, which is about 357 volts overshoot. And that can be a significant problem in the system, as it can cause damage on your power switch. So each power switch, silicon carbide switch, IGBT, whatever it might be, has a maximum drain source voltage, and any voltage approaching that or beyond it can affect the overall reliability and lifetime of the power switch, even causing permanent damage, which is why it's important to limit that drain source over voltage. It is also relevant with respect to electromagnetic compatibility, because the faster rising and the more ringing from this overshoot, the more radiated and conducted emissions there can be in the system. So moving on to our next slide, we have some experimental data which shows traction inverter switching in different operating conditions. So this data was taken using our traction inverter reference design driving an inductive load. So we tested a variety of operating conditions from 400 volts input to 900 volts battery input, and output currents ranging from 100 amps to 450 amps, and using both strong and weak drive strength. So in this figure, we have 700 volt batteries in the squares, 800 volt battery or bus voltage with the circles, and then strong drive strength is blue, and weak drive strength is red. And then we have in the top plot drain source voltage, and in the bottom plot module power losses. So you can see some clear trends as the output current increases. Power module losses trend upward, and drain source overvoltage also trends upward. But you can see that there's some differences between the strong and weak drive strength. With strong drive strength, there's always higher drain source overvoltage as compared to the weak drive strength, everything else being equal. And with weak drive strength, there is always greater power losses than strong drive strength, everything else being equal. So depending on the different conditions, in this case, particularly the output current and the current battery voltage, you might need different drive strengths to stay below this limit right here, the 960 volt maximum drain source voltage of the power FETs. So if you were to be operating with 300 amps and your bus voltage is 800 volts, you would be exceeding your limit right here. So you need to actually use weak drive strength to stay below your drain source, which would cause an increase in power losses of almost 2 kilowatts, or sorry, 1 kilowatt, which is quite significant. However, if your bus voltage is lower, you could use your strong drive strength the whole time, because you never do reach your drain source voltage limit. So this illustrates how your battery voltage and your load current both affect what drive strength is optimum for the specific operating condition. So to summarize, switching losses and voltage overshoot both increase as the load current increases, and then battery voltage, as the battery voltage increases, there's less headroom or less room for overshoot before reaching the drain source voltage maximum limit. So more overshoot headroom means that you can get away with stronger drive strength, which reduces your power losses. But if there isn't much headroom because your battery is freshly charged, you might need to use a weaker drive strength. Another condition that isn't represented in this plot, but is still important, is temperature. Because of the physics of power switches, lower temperature leads to a reduced safe operating area for the drain source voltage. So your safe limit might move down to more like 900 volts instead of 960 volts, which would mean that you'd need to use lower drive strength at that lower temperature until the power modules and system warmed up. So that's another condition to take into account. So how does this apply to a real system? Why would you need to design for all these different conditions? To address this, I want you to think about your typical commute to work. So in your commute to work, you're not driving at a constant speed with a constant acceleration all the time. Your acceleration and speed are going to be varying. Maybe you're idling at the beginning of your drive as you are just sitting in your car, maybe connecting your music, choosing which podcast you want to listen to. Your traction inverter isn't actually doing anything, so it doesn't have any output current. That's what we have plotted here. We have the inverter peak current plotted versus time, and this time would be the time on your typical commute. So this initial point, you're just idling, so your traction inverter isn't working. And then you accelerate out onto the street, so you get a little bit of a peak in your inverter output current. But then as you keep going through residential roads, maybe you stop at a stoplight here, stop sign here, deal with a bit of traffic before getting on the highway. But then you're accelerating to get up to speed on the highway right here. And then as you continue on, you hit some traffic. There's a little bit where you're just coasting right here because you hit the brakes, or you're decelerating right here on the off ramp. But then right here, you accelerate a lot. Maybe you had to get around someone, past someone, before finally stopping at the parking lot of wherever you work. So the point of this is that the usage of the traction inverter and the output current and operating conditions all change throughout a typical drive of a vehicle. And without adjustable gate drive, you would need to design the system such that in the worst case, so this peak right here at cold temperature with maximum battery voltage would never exceed the drain source voltage of the power module or cause any problems with the system. However, that leaves you a lot of room. All this area right here where you spend like 95% of your time, it means that you're using a weaker drive strength than you could otherwise, which leads to additional power loss. So during this time, lower than about 300 amps, with adjustable gate drive, you can have your traction inverter using the strong gate drive, which leads to significant switching energy savings. However, you can have logic to switch to the weak drive strength for any point above that threshold, preventing any damage and extending the lifetime of your inverter while still balancing it with power savings. So this is the advantage of adjustable gate drive strength. You don't have to design for the worst case conditions anymore. You can design for the typical operating conditions where your vehicle spends the most time, and then have a separate design, the weak drive strength, to account for all the worst case conditions. As an example of this, when would you use weak gate drive? You'd use weak gate drive when you have a high load current above the 300 amps in that last example. You'd use it when you have greater than 80% your peak battery voltage. So you've just charged up for a long road trip and maybe your battery voltage is really high, giving you less headroom. Use it in cold temperature until your car warmed up. And in all of these conditions, you'd be protecting the overall traction inverter and leading to greater reliability by using the weaker gate drive strength, which means that it takes longer to turn on the power module, and so there are increased power losses, but that's okay because we've designed for it and are using the weaker gate drive. And then when we get to our more typical operating conditions, the low load current or typical load current, and we have a slightly lower battery voltage, and the traction inverter is warmed up to a more typical condition and isn't really cold anymore. At these points, we can use the strong gate drive strength, really optimizing our switching losses to reduce the power consumed by the traction inverter. And this is what leads to increased range and efficiency, and then while still maintaining the reliability in stressful conditions. Looking at some more data, we have a couple more plots of turn on and turn off energy on the left, and then drain source voltage on the right. So we have in blue the weak drive strength plot as output current increases, both of the turn on, turn off energy and the drain source over voltage. They both increase as expected. And then we have the same plots, but with strong drive strength in red. And if you look at this with weak drive or without adjustable drive strength, you're going to have to always use the blue plot because you need to stay below your threshold across all your conditions, which means that you can't have any of the additional energy savings you see right here. But with adjustable gate drive strength, you can use your strong gate drive strength all the way up across different currents until you reach your overshoot limit, so your threshold. And then once you hit that threshold, your MCU sends a command to change to lower drive strength. And then your output current can keep increasing, but you're not going to be stressing your power modules. This means that below 300 amps, you can have all this power saving. That's up to 20 milliamps per switching cycle, which at high frequencies is quite significant. But you can still keep operating up to those higher current levels by just switching to the low drive strength. And then in a typical operating condition where you spend 90% of your time between 0 and 300 amps, you get all this energy savings in this triangle right here with no downsides. And that can lead to significant increases in your range and reliability. So the traditional output structure must be optimized just for the worst case overshoot, which will impact your nominal switching losses in this area I've already highlighted. But adjustable drive strength implementation allows optimization of switching losses across the whole current range, so both at worst case and in your typical operating conditions. Now, because for engineers, we all like real waveforms. So we have some test waveforms right here. We have the blue down here is the current increasing with each switching cycle. So this is the output current slowly increasing and trending upward. And then as the current increases, we actually use the GPIO to change the gate drive strength. So that happens here. At this point, we changed from strong drive strength to weak drive strength. And you can see that before that change, we have a lot of ringing on our switch node, so the drain source voltage. And it actually increases to a max drain source voltage of 1071 volts. But by just changing that one GPIO signal to weak drive strength, we see significantly decreased switching transient. So a max of only 991 volts. That's almost 100 volts difference just by changing that one GPIO. And at this point, we actually have 50 amps higher current, which would typically mean a higher overshoot. But that's controlled with our adjustable gate drive. And I've got zoomed in of the same waveform right here. So this is the strong drive strength with 300 amps with about a 1080 volt overshoot, and then a good amount of ringing, which can be okay, but any more is going to exceed our limit. But then in this next slide, we've changed to weak drive strength, which slows down the switching and increases switching losses, but now we've got margin again, so we can keep increasing our current, and our overshoot is only 991 volts, and there's significantly less ringing. This is the trade-off of adjustable gate drive, and you can really see the benefit between these two. The high peak and lots of ringing here, as compared to the nice soft peak that is much lower and doesn't stress our power modules right here. So the next question is, what does the implementation logic of this look like? How would you go about designing those different parameters? So we've identified a couple of key control parameters in an adjustable gate drive circuit. The first is the phase current. So this is measured in the system and is already measured in your traction inverter system because it's part of your main control loop. The second part is the threshold current. So this is the point where you would switch over between your low drive strength and high drive strength. This needs to be experimentally determined based on the overshoot of your hardware, the parasitics of your hardware, and then also the external conditions. So the actual battery voltage at that point of time and the temperature that can be implemented with a lookup table based on test results in the actual car. The next component are the actual drive strengths. The weak drive strength and strong drive strength are each determined by the values of the gate resistors on the weak drive outputs and strong drive outputs respectively. So choosing those gate resistor values is also an important part of the design. Once you have these parameters, you can implement a simple logic loop where the controller takes the current phase current and compares it to the programmed threshold. And if the phase current is greater than the current threshold, then the MCU tells the gate driver to use weak drive strength, either using the GPIO or an SPI command. If the phase current is less than I threshold, the gate driver can use the strong drive strength for maximum efficiency and power saving. So this simple logic is all that's necessary once the system's been characterized and the current threshold has been determined. So what this looks like, for example, in a typical drive cycle is right here. So you'd select the threshold such that the majority of your time, the nominal system based on the use case of the cars you're designing and the traction inverter is below your current threshold. And then adjust that level. You can do it experimentally to try and reach the maximum efficiency. And then from there, that lets you balance the switching losses and the overshoot. So as we see here, the spot we've seen before, as current increases, your switching losses and your drain source overshoot both increase. So you would choose this to pick a point somewhere on this plot to maximize the trade-off between turn on and turn off energy losses and drain source overshoot. And then a lookup table for the current threshold can be used to account for different system conditions, such as the battery voltage and cold temperature, really taking into account the worst cases and making sure to use weak drive strength whenever necessary to ensure long lifetime of the system and prevent any unexpected conditions. Now, the next question is, how do you select the strong drive strength and weak drive strength? The weak drive strength is actually easy. If you've ever chosen the gate resistance for a system without adjustable gate drive, that gate resistance, that same procedure is what you'll follow for the weak drive strength resistance. It should be chosen such that in the worst possible conditions, the overshoot is just below the designed drain source maximum voltage. This prevents any damage in the worst case conditions, but will have a trade-off of some power losses. And then the strong drive strength should be chosen to minimize switching losses during your typical conditions, not having to worry about those worst case conditions. And with that, I have one more addition for further optimization. So what we've discussed previously isn't necessarily instantaneous control. It more looks at the peak output current. So just the top of the sinusoid, and makes a decision based on that. However, with a modern controller such as TI's C2000 or Cetera controllers, you can actually adjust the gate drive strength each switching cycle or each current cycle. So if you have a fundamental frequency of 200 hertz, you can change 400 times per second to use a strong drive strength during this portion of the current output and a weak drive strength during the peak portion to prevent any overshoot. And this would be the way to even further optimize the benefits of adjustable gate drive strength. And with that, we've reached the end of our presentation. If you have any further questions, please stick around for a Q&A, and I'd love to discuss with you. Put your questions in the Q&A box, and we can have more discussion about how to use adjustable gate drive strength and integrated gate drive features to reach the system goals of high power traction inverter design. Thank you for your time, and I look forward to working with you.